Good morning, class. Today I'd like to speak briefly on what is known as a CMOS inverter. Many of you have seen a product like this one on the screen. This is a dual inline, it's often called a DIP package for an integrated circuit. These integrated circuits are relatively small, and this particular technology, the dual inline package technology, is not as common as it used to be, but it can still be found in many electronic equipment. On the inside of this package is going to be a variety of digital components, and the one that we'll examine briefly today will be the CMOS inverter. So the question becomes then, what is CMOS? CMOS is an acronym that stands for Complementary Metal on Oxide Semiconductor. And the reason that it is considered complementary is because there is a type of transistor known as the NMOS transistor, and there is then the complement, which is known as the PMOS. So the N stands for negative and the P stands for positive. And these N's and P's designate whether or not we are going to be using the transistor as either being inside of a substrate whose polarity is positive for the NMOS device, or their substrate that will be negative for the PMOS device. And as we see, there is going to be three terminals to consider for each of these devices: the source, the gate, and the drain. And for the other transistor, again, a source, a gate, or drain. And then for each of these, their substrates will either be connected to a ground, or will be connected, in this case for PMOS, to a high voltage, the highest voltage in the integrated circuit. And what we will discover is that, properly connected, current will be allowed to travel when the transistor is attempting to turn on by making the gate voltage high with respect to the source. In our case, the NMOS will be connected to ground, as we'll see in a minute. This drain will be connected to this source or this drain because it is a symmetric device. These two gates will be connected together, and this either source or drain again will be connected to high, which will also be connected here. Now, with that conversation, it's easier to illustrate this interconnectivity using a schematic. So here we have a schematic view of what's inside of our integrated circuit. You'll see that our two gates are connected together, and you'll denote that the P was denoted by a circle on its gate, and the N device, no circle. You'll notice that there's a separation between the gate and this channel, and the channel is this area right here. So these two gates are connected together, and then a drain and a source are connected together, and then one source connected to ground, one drain connected to, in our case, VDD, as we see here, and then a drain and a source connected together. So these are our power supply connections. We will have one input and one output. How do they look on the inside? Here is a called a Manhattan geometry for the layout of an integrated circuit, the layout of the inverter that we saw just a minute ago. And we'll notice that here is our substrate, and our substrate is connected through a contact through metal, and it will be connected to ground. This N diffusion will be connected through a P diffusion, again to ground, as we saw in our view here. Source connected to substrate, and it will be connected to ground. Here our source connected to substrate, connected to VDD. Our drain connected to substrate, connected to VDD. and then finally in to out. So what kind of response do we expect? What we expect when we connect our in to a positive voltage is that we will get a negative output. So notice here Vn sweeps from 0 to 5 volts. Our VDD is connected to 5 volts. Our ground is 0 volts. And as we sweep the input from 0 volts to 5 volts, we'll discover that the output goes from 5 volts through a transition region to ground. And so we say that the output is the inverse of the input. If the input is 0, then the output will be 5. If the input is 5, the output will be 0. And so we get here the concept of a high or a low, or a 1 or a 0, as we understand in digital terms.